Hello, everyone, and welcome back. So now that we have got the discussion over normals and our cheating yet somewhat elegant implementation behind us, let's go ahead and move into some talk about tangents.
I don't know. Should we call it cheating or should we call it creative thinking?
Creative thinking.
Yeah. So we're just thinking outside of the box when we decide to implement our normals. So with that in mind, we're going to do the same thing with tangents. Now, what is a tangent? Why do we care? And why do we need it? If I go over to Photoshop again.
You might need my help, it looks like.
Yeah.
There we go.
All right. So let's say we've got Photoshop. And let's see, can I do this way? I would break out the tablet and the pen, but I saw what that drawing looked like yesterday and decided I'm not going.
It wasn't that bad.
All right, so let's draw a sphere. All right, now a vector or a normal, like we were showing yesterday, is a line that is perpendicular to a point on a surface. So that would be the normal of this spot on the sphere.
Okay.
Now, a tangent is going to be another vector that is perpendicular to the normal of that point on a sphere. So where we've got the sphere and we've got our normal, the tangent to it is going to be a vector perpendicular to the normal. Now, in this case, we've got one vector, and I really have to turn off the square. It's driving me crazy for the show remote cursor. But so we've got a vector that is tangential to the surface.
Okay.
Now, this vector doesn't just point in this one direction. There are many tangential vectors that go in a 360 degree around from this point on the surface because they're all tangents to the normal in all 360 degrees. So if we were to look at this kind of like a top-down, so let's see if I can come up with something that looks like a top-down version. So if I were to stroke this with 2 pixels of white, hit Control D, let's get my brush out, and if I were to draw a dot in the very center, that's kind of small. Let's make a bigger dot. So hopefully that'll show up. So let's say the dot is the normal, that is this vector that is facing straight up. Now this vector that we drew here is the equivalent of a vector that hits that point on the surface and radiates out by 1 unit. So it's a unit vector. But this is only one possible tangent. That's a possible tangent. There's another possible tangent. Here's another one. And it's starting to look like a pizza, which is making me hungry again. But so there are, in theory, an infinite number of tangential vectors from this point on the surface. We only want one, and we need it for lighting calculations. So which one we pick doesn't really matter, but it is nice if we choose one that lines up with our mesh. So we know with our mesh that it's drawn, if I create a new layer here, it's drawn with our Y or our Y-axis coming out of the camera, our Z-axis facing up. Yeah, that worked. I'm still on the line tool. So here's Z. Here's X. Well, that's a weird symbol. That's more like a lambda.
Yeah, it works.
Yeah, there's an X. So, but this also corresponds to our U direction and our UV layout, and this corresponds with our V direction on our UV layout. So what we want to do is we want to set up, while we're calculating our tangents, that our tangent is in the direction of one of these two axes. It doesn't matter which one we choose as long as we're consistent with each and every one of them. For the our train system, because I know everything is equally spaced and it will always be lined out like this. The only difference is the height of each vertex. I want to set it up so my tangent is going to be calculated from the point of the vertex along the z-axis. So all of our tangents are going to be calculated this way. And then our normal is going to be whatever is calculated coming out of the vertex based off of our little creative thinking process in the last video. And we'll calculate a bitangent, sometimes called a binormal, but technically it's a bitangent, which would be another vector that is perpendicular to both the normal and the tangent. Kind of hard to see here, but if I were to go back to this diagram, so let's say here, I'll change the color. That should help. Let's pick a red. All right, so if we're calculating our tangent as being along the z-axis, so this is our tangent, our normal being the vector that's coming straight out of our surface straight up here. And I want to calculate our bitangent. Our bitangent is going to be the one that is perpendicular to both of these.
Yeah, careful with the blue on the blue
Yeah, it's like
background.
going, hey, how about blue on blue? That was not the best choice. How about green? Let's see if that works. That's not much better. Purple. I don't know, make it go out a little bit further. That's a little bit better. So the vector that is perpendicular to both the tangent and the normal is your bitangent. And this is also used for some more advanced lighting calculations. So that gets into why do we need it? We need them for lighting calculation. What do I mean by that? If we go into Unity and let's make some changes based off of the project that we did last time. We'll go into our materials, bring up our test material. We're going to remove our green grass texture so it'll make it easier to see what's going on. And we go ahead and run this. So give it a sec to come up. And you can see if you want to look around for me because it won't respond.
Sure.
We do have lighting information. We can see that there is diffuse lighting on this texture. So that is being calculated based off of our normal. We've calculated the normals in such a way. We've kind of got some liberal playing room with adjusting the Y element of our normal to give us more or less shadowing. So we're playing with that, kind of faking slope, or we're doing slope lighting or faking self-shadowing on the hills. But that is only one possible way of doing lighting calculations. Something else that would improve the way that this looks overall is if we used bump maps or parallax diffuse maps, if you would. In the case of this video, we're going to demonstrate with bump maps because I'm not really happy with the shaders for the parallax maps that are built into Unity. They have some flaws with them. So when I start messing with shaders, I might play around and see if I can't get something that looks a little bit better. I'll show you later once we get everything implemented, the problems that we get with it. But if we go to a bump diffuse, we're going to leave our base texture empty because I want the white to show up, but I want to put a normal map in. So we're going to go into textures. If you've been following along, you should have a height map that we used when we initially started generating the terrain before we switched over to world data. We're going to take that height map texture and we're going to repurpose it. We're going to go ahead and turn it into a normal map. So we're going to generate it from a grayscale. We're going to set its bumpiness down to 0.2. And the max size, we're going to drop it down to 512. We don't need a full 2K for the normal map. With those settings, we can hit apply. Give it a sec to calculate, and we get a normal map with it. So if we go back to our UV test material, we can go to our normal map, find it, which will be this height map that we just created. And we can assign that. So we get here. We can see that it looks like a bump map applied to our preview window. Now the problem happens though is if we hit play, give it a sec to draw up, we can see that it's added something to our map, but it doesn't look anything like a bump map should.
And no, it's more of a almost a marble look.
Yeah, it's almost like a decal that got it onto our white. Does not give us the look we're going for at all. And the reason why is we don't have enough information to calculate the bump map for the lighting information. The missing information that we need is that tangential information. We have to calculate tangents for our bump map to work correctly. So without that information, and I'm willing to bet most of the people who've been following through the train system already have gone through and go, oh, great, I'm going to put a bump map on. And I've already done it and go, I don't see any bumps. What's going on? So, and I do have to give kudos again to another one of our members, because when we first started going through the train system after, I think it was the very first session we put together, member JJ Guzzardo threw up a post, and he had gone through and put together a method to extend the mesh class inside of Unity to be able to calculate tangents.
Okay.
So I do want to thank him for that, because for a long time that was the method that I was using for calculating tangents, so I didn't have to go and do any research. So, and I do want to point out how those calculations are done, because that is more of the, well, actually it is the correct way to calculate tangents, but it's not our creative way that we're going to be using. But if we go over into Firefox real quick, the example that we're going to be showing is also a link that JJ Guzzardo put up that also references this book. And this is a book I have on my shelf. It's very good. It goes into a lot of the mathematics that you need to know if you're going to be a game programmer, particularly 3D game programming. But it goes into normals and tangents and lighting models and a bunch of really, really cool stuff that is a definite need to know if you're going to be doing this. So, good book to have. I just wanted to point it out. Not that we're, touting any particular site, but
well, everybody knows Amazon. I mean, that's just kind of the go-to place.
Yeah. But the link that JJ gave us was to this site, and this is the a more traditional way of calculating out tangents. Basically, what you're doing is you're calculating your tangents based on the three vertices that make up a triangle, as well as their UV layouts, calculating the contributions of the UV points, along with your tangents and your bitangents, going through some matrix and dot product math to derive your final results. and it goes into loops and quite a bit of calculations, as you can see.
Mm-hmm.
So it can get fairly complicated, and the results can, depending on the size of your mesh, take a very long time and slow down your system.
So did you use this implementation?
Yes.
Okay, so you did at some point?
Yeah, I use this from basically the day that JJ posted this
Mm-hmm.
up until about a week or two ago when I started redoing the normals,
Mm-hmm.
because I knew that the normal calculations weren't going to work across patches. So I had finally gotten some free time to deal with that problem. So when I was dealing with that problem, came up with a solution and realized that that same type of solution can be applied to the normal calculations.
Mm-hmm.
Or not the normal, but the tangent calculations. I redid my tangent code as well.
Gotcha.
So this, now, I'm not saying that we should use the technique that I'm going to show you for the train for all tangent calculations. What we're going to show you in the next video is highly optimized based on the fact that we know exactly what the mesh of our train looks like, and we know it's always going to be like that. It's not going to change. This type of calculation is more valuable if you're using it on meshes that you don't know what the geometry is going to look like,
Mm-hmm.
where it's, let's say, a 3D model where you've got vertices that are wrapping around surfaces that are tucked under and your UVs are changing directions.
Okay.
That is something that our terrain doesn't do. We have no overhangs. We have no caves, no cliffs. Well, we've got cliffs, but we have no overhanging cliffs.
Right.
We always know that our terrain, no matter what we do to it and how much we displace the height of it, it is always going to be laid out equally spaced and made up of initially equilateral triangles until we start displacing the y. So we know this is always going to be true. The other thing that is always true with our terrain is the fact that once these UVs are mapped, no matter how much you displace a vertex vertically up or down from the surrounding vertexes, those UVs are not scaling. They're not shifting around. They're always going to be the same.
Mm-hmm.
So based on those two facts, I'm going to be able to make some very basic assumptions, and with a couple of calculations, I will be able to say that this the tangent will always be in this direction, and I can calculate the bitangent the same way when I need it. Right now, I'm not. I will calculate it so I can demonstrate it inside of the system, but I'm not going to calculate and save it into an array, because Unity's system itself doesn't have a mechanism for saving the bitangents. So that if we need them, that will be something that we'll calculate shader side.
Okay.
Now, that also gets us into an interesting discussion that we had brought up way back in the beginning of the series, is why do we have to calculate tangents at all? Doesn't Unity provide a mechanism for calculating tangents? They provide one for doing normals, so why not tangents? They do and they don't. There is a mechanism for calculating tangents on meshes that you import in the traditional way into Unity. So if you import a mesh, a model into Unity, there are a couple of sliders that allow you to adjust how tangents are calculated for those meshes. If you decide to create your own custom mesh, like we're doing with the terrain patches, there is no built-in way of calculating the tangents. It's like I think it's just that Unity thinks if you're smart enough to figure out how to make your own mesh, you should be smart enough to make your own tangents.
Right.
So we have to do it ourselves. Now, we could do it the way that with the link that J.J. Abrams posted, which is pretty much the same.
J.J. Abrams was on our site? Awesome.
Yeah, J.J. Gizarro. I said that because you started calling him that in
Only
class.
in one class.
It only takes one class to get my head screwed up. I mean, you could sneeze and I'd lose my train of thought.
Fair enough.
But JJ Gazzardo posted that link, and we could implement tangents that way. There are other ways that you could do tangents. That's just one way, or we can implement it the way that we're going to do. So, and I'll talk more about how we're going to do it in the next video. Again, so let's see. With that, we've got a discussion on that. See, you derailed me already. I was
No,
going.
you're doing great. You're doing great.
So we've seen what it looks like here. I actually can't show a tangent because I want to be able to draw the tangents on the screen like we do with
normals.
With the normals, but we're going to have to make some more modifications. I'll do that in the next video.
Okay.
So we can demonstrate all that as well. I'm just trying to think if there's anything else that I wanted to cover in this video before we wrap up. So, but I think
you've got everything here.
If I miss something, I'll just bring it up in the next video.
Yeah, that sounds fantastic. Awesome job, Levi. All right, well, with that is going to conclude this video. Thanks a lot.